Good afternoon, students. Welcome to the 41 lecture of refrigeration and air conditioning subject. The last class we have discussed about the problems on psychrometric processes and the concept of ventilation of air conditioning. Today in this class we will discuss about the problems on indoor and outdoor ventilation and the introduction to the comfort air conditioning. A 100% outdoor summer conditioning system has a room sensible heat load of 400 kilowatts and a room latent heat load of 100 kilowatts. The required inside conditions are 24 degrees centigrade and 50% RH, and the outdoor design conditions are 34 degrees centigrade and 40 RH. The air is supplied to the room at the dry bulb temperature of 14 degrees centigrade. Find a required mass flow rate of the air. Find the required mass flow rate of the air. B. Moisture content of the supply air. C. Sensible latent heat loads on the coil. D. The required cooling capacity of the coil, cooling sensible heat factor, and coil ADB if the bypass factor of the coil is 0.2. Barometric pressure is equals to 1 atmosphere. Comment the results. The psychrometric process shown in this figure. See this figure. The psychrometric properties are the inside and the outside conditions are inside conditions వచ్చేసి T1. See from the question, the inside conditions are Ti is equals to Ti means T inside is equals to 24 degrees centigrade dVT and RHI is equals to 50%, and the outdoor is for 34 degrees centigrade 40 RH. Now, from the psychrometric chart, using the psychrometric equations, the moisture content Wi is equals to moisture content indoor is equals to 0.0093, and the latent heat Hi is equals to 47.66. Therefore, see here Ti that is indoor, Ts that is outdoor. So T out that is outdoor. Then the outside conditions Ti is equals to 34 degrees centigrade, RHI is equals to 40 degrees centigrade. From the psychrometric chart using psychrometric equations, the moisture content and the enthalpy of the inside air are W0 outside is equals to 0.01335 and H1 is equals to 68.21 kilojoules per kg. Next, what is the things you have to find? A. From sensible energy balance equation of the room, the required mass flow rate of the air Ms is equals to QSR divided by CPM Ti minus Ts, that is equals to 400 CPM value, Ti value minus Ts value. So 39.154 is the answer for the problem A. Next, B. The moisture content of the supply air is obtained from the latent energy balance of their mass. Ws is equals to Wi minus Qir divided by Ms into Hfg. So the value Wi is equals to 0.009 minus Qi 100 divided by 39 into 39.154 into 2501. That implies 0.0083. Next is C. From the energy balance, the sensible and latent loads on the coil is QSI is equals to MS CPM T0 minus TS. So MS into CPM into 34 minus 14, that is 800 kilowatts. And QIC is equals to MS into HFG, W naught minus WF. So the values W naught minus WS, the value is 494.5. The required cooling capacity of the coil is equal to the total load on the coil. QTC is equals to QSC plus QIC. So QSC 800 plus 494.5. This one, the 494.5. The value is 129.4.5 kilowatts. The coil sensible heat factor CSHF is equals to this one. The coil ADP is obtained by using the definition bypass factor as T ADP of 1 minus X is equals to Ts minus X of T naught. Therefore, Ts minus X into T naught of by the 1 minus X. That implies 14 minus 0.2 into 34 divided by 1 minus 0.2. That is 9 degrees centigrade. Next topic. Systems. Before we have discussed about systems with indoor air for ventilation. 100%. Now we'll discuss about systems with outdoor air for ventilation with zero bypass factor. Okay, zero bypass factor. See here, this is a cooling coil, the supply fan. So from the cooling coil, the supply fan, the mass of air is going inside with the T temperature indoor, mass indoor, and enthalpy, and from here it is going in this direction, Ti, Wi, Hi, right? So this graph shows that T indoor, T outdoor, T mass, outdoor, indoor. So the ADP, that is equal to temperature, is equals to at this point. So all the 2 points are intersected at this point. Next, the total conditions TSH, total conditions, total sensible heat is equals to room sensible heat plus OASH plus air, right? So the condition system gains include supply air and return, air fan gains, duct leakage, sensible losses, return air gains from lights. Therefore, the TLH is equals to total latent heat is equals to RLH plus OALH plus supply air duct leakage latent losses. GTH is equals to grand total heat, that is equals to TSH plus TLH. Okay, grand total heat is equals to TSH plus TLH. Now the GSHF is equals to TSH plus TSH divided by GTH. So what is the meaning of GSHF? GSHF is equals to the ratio of total sensible heat divided by grand total heat. Okay, total sensible heat divided by grand total heat. Next, sensible heat with outdoor air for ventilation with bypass factor. So here now it is outdoor. So earlier it is inside, now it is outdoor. When the mass is going in this direction, bypassing means it is not going inside the cooling coil. It is making an outside arrangement, bypassing, and it is passing into the supply fan and it is entering into the AC room. Sensible heat. From the AC room, the outside air is passing in this direction. From through this return van, the air is pressurized to force in this direction and it will come outside. Therefore, ME is equals to M naught. Later, the required temperature is coming down and again it is going into the cooling coil and it is bypassing. Okay. Now, the RSHF and ESHF and GSHF. So what happens when these are used for this outdoor and indoor concepts? Now the effective room sensible heat ERSH. Okay, the effective room sensible heat ERSH is equals to RSH plus BF into outside air SH. Okay, RSH plus BF into outside air sensible heat. Now the effective room latent heat load ERLH. Effective room latent heat load ERHH is equal to RLH plus BF into outside air LH. Now the ESHF is equals to ERSH divided by ERSH plus ERLH. ERSH divided by ERSH plus ERLH. Now the room sensible heat factor RSHF is equals to RSH divided by RSH plus RLH. RSHL is equals to room sensible heat load. RLHL is equals to room latent heat load. Next, the effective conditions. In the same way, whatever we have discussed, that is RHS, RLS. Here also we'll discuss about the effective conditions of indoor and outdoor air conditioning systems. Right? ERSH is equals to effective room load sensible heat, that is equals to RSH plus BF into XOASH plus air conditioning system gains. BF is equals to cooling coil bypass factor. BF is equals to cooling coil bypass factor approximately zero point 0.1 value. This includes the supply chain and return air fan gains, duct leakage, sensible losses, return air gains from the lights. Then ERLH is equals to effective room latent heat. Effective room latent heat. That implies RLH plus BF into OALH of plus air conditioning system gains. BF is equals to cooling coil bypass factor approximately 0.1, which includes the supply air and the return air fan gains, duct leakage, latent losses, return air gains from the lights. ERTH is equals to effective room total heat. So what is ERTH? ERTH is equals to effective room total heat, that is equals to ERSH plus ERLH. Now ESHF is equals to effective sensible heat factor, that is equal to ERSH divided by ERTH. Now see here what happens to the effective thing. So here the AC building having T inside, W inside and latent heat inside. So the RTH is equals to RSH plus RLH. So the M naught is passing in this coil heat bypass factor. This is a heat bypass factor. So it is going into the coil and going into the supply fan, and supply ducts are passing the medium into this room air conditioning. From here, through the return fan, it is going outside. So this is a cyclic process which happens in the indoor and outdoor systems for the effective conditions, right? Next, the next topic to be discussed is requirements of human comfort and concept of effective temperature. Okay, requirements of human comfort and concept of effective temperature. The thermal comfort, the thermal comfort, the conditions of mind which expresses satisfaction with the thermal environment is known as thermal comfort. A living human body, a living human body is nothing but a heat engine chemical energy. A living human body, heat engine chemical energy contained in the food. It consumes it continuously, converted into work and heat. So whatever the food we are consuming as a human body, whatever the food that is consuming, it is converted into heat and work. Metabolism, conversion of chemical energy contained in the food into heat and work is nothing but metabolism. Chapma. Metabolism is equals to conversion of chemical energy contained in the food. Conversion of chemical energy contained in food into heat and work is nothing but metabolism. What is metabolism rate? The rate at which the chemical energy is converted into heat and work. Here, the conversion of chemical energy contained in the food and work. But here, the rate at which the chemical energy is converted into heat and work is known as metabolic rate. At neutral condition, the temperature of the skin of human body is 33.7 degrees centigrade, or maximum temperature, core temperature which we will take is 36.8 degrees centigrade. Beyond that, the human skin will get irritated because of the temperature. Now, what happens when the major losses in efficiency happens? So the temperature maximum is 31 to 35 degrees centigrade, and the neutral temperature, the core maximum we reach is 36.8 degrees centigrade. That is at neutral temperature. Now beyond that, whenever it is passing, that is 39 degrees centigrade and 43 degrees centigrade, the temperatures are lethal. Okay, the temperatures are lethal and not predictable. So the slight discomfort happens between 35 degrees to 36 and 36 degrees to 39 degrees. So at this point, the major losses happens for the human body. Next, oxygen. Qgen is equals to Qsk plus Q Res plus Qst. So what is Qgen? The rate at which the heat is generated inside the body. Okay, Q generated, the rate at which the heat is generated inside the body. Qsk, the total heat transfer rate from the skin. The total heat transfer rate from the skin. Qres, the heat transfer rate due to the respiration. The heat transfer rate due to the respiration. Qst, the rate at which the heat is stored inside the body. Qst means stored, St means storing, Rs means respiration, Sk means heat transfer, and Qgen is equals to M of 1 minus efficiency into M. So the metabolism rate depends upon the activity measured in the unit metabolism, and the metabolism rate per unit area of sedentary person is equals to 58.2 W per meter square. Metabolism rate per unit area of sedentary person is equals to 58.2 W per meter square. Now, the activity what we are doing in a air conditioned room, based on that we'll see the specification and metabolism rate as per the temperature. We'll see now. activity for resting, walking, office activity for driving in a car, domestic activities, dancing, teaching, games and sports. So for resting, that is sleeping, reclining, seated quiet, standing and relaxed. So for all these things in the resting position, the metabolism rate for sleeping is equals to zero point 0.7 metabolism, reclining is equals to zero point 0.8, seated and quiet is equals to 1, standing and relaxed is equals to 1 point. So here, if you see the sleeping and standing, you can see the difference of zero point 0.7 to 1 point. Metabolism. And for walking, we are having 0.89 meters per second, that is 2 metabolism rate. And for 1.9 meters per second, we are having 3.8 metabolism rate. Now the office activity, the typing is equals to 1.1 metabolism rate, and for car driving, the metabolism rate is approximately 1 to 2 metabolism rate, and for driving heavy vehicles it is more, that is 3.2. And for cooking process, the metabolism rate is 1.6 to 2.0. Coming to the washing dishes, the domestic activities, the metabolism rate is 1.6. House cleaning, it is about 2 to 3.4 metabolism rate than that of the heavy vehicles doing. And for dancing and teaching, the metabolism rate is 2.4 to 4.4 and 1.6. And for games and sports like tennis and singles, we are having 3.2 4. Gymnastics we are having 4, basketball we are having 7.6, wrestling we are having more, that is 7 to 8.7 metabolism. So like this, the temperature, that metabolism rate changes depends upon the activity what you are doing. Next, the total heat transfer rate from the skin QSK is given by QSK is equals to plus or minus Q conventional plus radiation plus Q evaporation. Therefore, Q conv is equals to heat transfer rate due to the convection process. Convection means that is sensible heat. Q transfer heat transfer due to the radiation. Q evaporation heat transfer due to the evaporation. Evaporation under latent heat. Convection under sensible heat. Sensible heat, latent heat. Right? Next. A sedentary person at a neutral condition loses about 40% of heat by evaporation, about 30% by convection, and 30% by radiation. Due bias equation, A is equals to 0.202 m into h. ADU is equals to surface area of a naked body, in meter square. M is equals to mass of the human being, and h is equals to height of the human being in meters, right? So the due bias equation, A is equals to 0.202 mass of the human body into height of the human being. Next, when the environment is cooler than the neutral zone, what happens? The body loses more than is generated. When the environment is colder than the neutral zone, then the body loses what? More than the heat what it is generated. Then the regulatory processes in the following order will take place. Zone of vasomotor regulation against cold, vasoconstriction. Blood vessels adjacent to the skin constrict, reducing flow of blood and transport of heat of the immediate outside surface. The outer skin tissues act as insulators. So whatever the tissues that is present on the outer skin will act as a insulators. Now the zone of metabolism regulation. If environment temperature drops further than that of the body, then vasomotor regulation does not provide enough protection. So, through a spontaneous increase of activity and by shivering, the body heat generation is increased to take care of increased heat loss. Now, the zone of inevitable body cooling. If the environmental temperature drops further than that of the metabolism regulation, so here we are having zone of vasomotor regulation. Here we are having zone of metabolism regulation. Here we are having zone of inevitable body cooling. So if the environmental temperature drops still further, then the body is not able to combat cooling of its tissues. So the body temperature drops, which could prove to the distressous. This is called the zone of inevitable body cooling. This is called the zone of inevitable body cooling. So we are having three things, that is the zone of vasomotor regulation against cold, the zone of metabolism regulation, the zone of inevitable body cooling. Now, when the temperature is in hot condition, okay, when the environment is hotter than the neutral zone, then the body loses less heat than generated. Now, the regulatory processes occurs in the following order. So, what are the processes occurs when the environment is in hotter condition? Zone of vasomotor regulation against heat, zone of evaporative regulation, and the zone of inevitable body heating process. So, we'll see each one by one. Zone of vasomotor regulation. Here, the blood vessels adjacent to the skin dilate, increasing the flow of blood and transport of heat to the immediate outside surface. The outer skin temperature increases, providing a great temperature for heat transfer by convection and radiation. That happens in this zone of vasomotor regulation. Now, coming to the zone of evaporative regulation, if the environmental temperature increases further, what happens? The sweat begins to start. The sweat glands becomes highly active, drenching the body surface with precipitation. Now, what happens? If the surrounding air humidity and air velocity permit, then the increase in the body temperature is prevented by increased evaporation from the skin. That happens when it is evaporator regulation takes place. The zone of inevitable body heating. So what happens when the zone of body heating takes place? If the environmental temperature increases further, then the body temperature increases, leading to the zone of inevitable body heating. The internal body temperature increases, leading several ill effects such as heat exhaustion with symptoms of fatigue, headaches, dizziness, irritability in the body, heat cramps resulting in the loss of body salts due to the increased perspiration, and finally heat stroke అంటే ఎండ వడదెబ్బ కొట్టడం, heat stroke could cause permanent damage to the brain. That is one thing. Heat stroke వడదెబ్బ కొట్టి కొంతమంది చనిపోయారు అంటారు. So why? Because the heat stroke will directly attack the brain, thereby there will get a damage in the brain, or could even be lethal if the body temperature exceeds 43 degrees centigrade. So 36.8 is maximum temperature what a body can resist. Beyond that, we should not be in the outdoor, right? Next, the next topic is purpose of comfort air condition system. So why we need, what is the purpose, right? We'll discuss these things. The purpose of human comfort air conditioning system. The human body possesses a regulatory metabolism. Beyond that, certain conditions it becomes ineffective. Together, so generally the human body possesses a constant regulatory metabolism rate. When it disturbs, what happens? The conditions will become ineffective and the body will get some changes. It is essential to ensure that surrounding conditions are conducive for comfortable and safe living. Then what we have to do? So whenever the body will become ineffective, will get damage to our or harmful to our body skin. So for that what we require, we have to ensure the surrounding conditions to be conductive. So మనకి త్రీ టైప్స్ ఉన్నాయి: conductive, convection, radiation. So it should be in a conductive in a state for comfort and safe living, right? For a comfortable and safe living. To provide suitable conditions in a occupied space so that it is thermally comfortable to the occupants. So what is the point here? To provide the suitable conditions, to provide suitable conditions in occupied space so that it is thermally comfortable to the occupants. So we have to provide a suitable temperature whenever the occupants are more in a thermally comfortable space. The objective of the comfort air conditioning system is to control the environmental factors so that comfort conditions prevail in the occupied space. So finally, so the main objective of the comfort air conditioning system is, so the main objective of the comfort air conditioning system is to control the environmental factors so that the comfort conditions prevail in a occupied space. Therefore, it has no control on the psychological and insulation factors. Therefore, the wearing suitable clothing may help in reducing the cost of air conditioning system. So whenever there is a changes like that, so we have to go with the changes. We have to go with the changes by wearing suitable dress so that we can reduce the cost of air condition system. Next, what are the factors affecting the thermal comfort? Next topic is what are the factors that will affect the thermal comfort. The various factors that are affecting the thermal comfort are: first one is psychological factors. Okay, the physiological factors. The physiological factors are nothing but the age of a person, the activity what he is doing, what type of nature of a person he is, and the gender. Sex means male or female, and the health conditions of a person. These influence the metabolism rate. Okay, these influence the metabolism rate. The most important is activity. The most important apart from the age, gender, health is the activity what is doing. Other factors have negligible effect on thermal comfort. Other factors means the age, activity, the age, gender, and health have the negligible effect on thermal comfort. Next point. Insulating factor due to the clothing. The type of clothing has strong influence on the rate of heat transfer from the human body. The unit for measuring the resistance offered by clothes is also called clo. In the short form, we are calling the clothes as clo. One cloth is equal to the resistance of about 0.155 meter square. The typical clothes value for different types of clothing have been estimated. For example, a typical business suit has a clo value of 1, while a pair of shorts have the clo value of 0.05. Means depends upon the thickness of the material. the typical business suit. See here, the typical business blazer or suit, whatever the person is wearing, has a clothing value of 1, whereas the pair of shorts have the clothing value of 0.05. Okay. Next, environmental factors. So say physiological factors and insulating factors due to clothing and environmental factors. The dry bulb temperature, relative humidity, environmental కిందకు వచ్చినప్పుడు the dry bulb temperature, environmental relative humidity, air motion and surrounding surface temperature. Of all these, the dry bulb temperature affects heat transfer by convection and evaporation. Among the dry bulb temperature, relative humidity, air motion and surrounding surface temperature, the dry bulb temperature affects by convection and evaporation. The relative humidity affects heat loss by evaporation. The air loss influences both convective and evaporative heat transfer, and the surrounding surface temperature affects the relative heat transfer. Therefore, the other factors what they are affecting is traps, asymmetrical cooling or heating, cold or heat floors, also affects the thermal comfort. Then the operative temperatures for this factors affecting the thermal comfort. T operative, this factor is the weighted average of air, DDP and TMRT into the single factor, and it is given by top is equals to TOP, T operation is equals to operative temperature is equals to H into TRMRT plus H into TCAMB is equal to TMRT plus TAMB ambient temperature, where HR and HC are radiative and convective heat transfer coefficients and T ambient is equal to DDP of the air. Now the effective temperature ET. This factor combines the effective of a dry bulb temperature and air humidity in a single factor. It is defined as the temperature of the environment at 50% RH, which results in the same total loss from the skin as in the actual environment. Since this value depends on the other factors such as activity, clothing, air velocity, and TMRT, standard effective temperature TSET standard effective temperature is defined for the following conditions. Therefore, the clothing 0.6, activity 1 point, air velocity 0.1, TMRT in Kelvin. So if you see in a winter zone, so if you see the graph between the T operative and the W, the mass, okay, so the DTP value is equal to 2 degrees centigrade and the effective temperature at 26 degrees centigrade. For a winter zone, it is shown in the blue color portion. See the winter zone, it is at blue color portion 20 degrees to 22.5 degrees centigrade, and the summer zone is beyond the 22.5 degree. The red color portion shows the summer zone which is beyond 22.5 and at 26 degrees centigrade. That is at this graph. Okay, this graph. The inside design conditions for winter. In a winter season, the inside design conditions are T operative is equals to 20 to 23.5 at RH of 60% and T operative between 20.5 to 24.5 degrees centigrade at DTP of 2%. The inside design conditions for summer season is equals to T between is equals to 22.5 to 26. Mana graph patti we have written the sentence 20 to 23.5, 22.5 to 26. At RH is 60 degrees, at RH is 60 degrees. T operation between 20.5 to 24.5. T operation is equal to 23.5 to 27 degrees centigrade at DTP of 2 degrees centigrade. The season is winter. In a winter season, heavy slacks, long sleeve shirts and sweaters we have to wear. For that, the temperature is zero point 0.9 clothing and T operative is 22 degrees centigrade, and the T operative range for 90 degrees acceptance is equals to 20 to 23.5 degrees centigrade. And coming to the summer, light slacks and short sleeve shirts, zero point 0.5 clothing, 24.5 degrees centigrade, 23 to 26 degrees centigrade. For minimal shorts, ICL is equals to 0.05 clothing and T operative is equal to 27 degrees centigrade, and the T operative range is equals to 26 to 29 degrees. Okay, so with this we'll stop the class. We'll discuss the next topics tomorrow. So in this class we have discussed about the indoor and outdoor temperatures, comfort air conditioning systems for indoor and outdoor systems, and what is the concept of RSH, EFH, effective conditions on the load calculations of a room temperature, right? So thanks for listening to the class. Have a good day.